news that maybe you weren't familiar, or you knew, or didn't know, is I got the go ahead that I can put this code online as long as I attribute this to the book. So I did. So here is the code for that. There's a little fuzz on my mouse or something. So the code's now online. I noticed there's somebody in the chat, so I will post a quick link. Well, I don't even have to really post it. I can just do this, and you can get the links to the books. I shouldn't have deleted that, but that's okay. So we're gonna have a tree of a int to tree in. Oh, but we want integers. Excuse me. Yeah, but I like it. I like integers. Yeah, I mean that's fair. Actually, we should be getting autocomplete, shouldn't we? Okay, there's. What's the error here? We should be able to. Okay, it seems okay now. So, yeah, if we have a leaf, we want to return. Oh. Oh, I see. It's embedding the integer in here. So you'll just start it at 0 instead of using a go function, which I suppose is fine. Yeah, now we have what we need. I thought I had this before. I guess I didn't have this code before. What is this complaining about? Oh, okay. It's not complaining. I thought we had this code before. Did we not? Maybe I just didn't write it correctly. I don't remember. Because this would have just been replaced with our go function. I thought. Let's try it again. Because I'm confused. I thought I wrote this code before. Oop. Well. Yeah. I don't couple the result. That's the difference. I need that. Right. I didn't write the state. Duh. Oh, yeah, absolutely. Sorry. Yeah, please ask me that as soon as you need it. That's a little too big. How's that? Okay. So basically, in this case, we're adding this little pair here, which we didn't have before. So what if we write it in the Go style? Or Go function style. Let's do that. So I just didn't do it correctly. T, Go T. It's fun to say Go T. So we need to take a tree, integer, create a tree, integer a integer, right? I mean, this is trivial. I don't know why I'm doing this. We already wrote this code, so okay. So yeah, that's basically all we need to do. And really, I suppose we should do this backwards. I should use relabel, but I didn't. Let's fix that. It won't let me because of this one, so I assume. Nice. So this is probably what we want, I think. For anyway, writing this in the crappier way. Okay, so I think what I was doing last time was just not keeping the integer around correctly. So when we did basically these two pieces, I don't remember what I wrote because I deleted it like a doofus. But when we wrote this, essentially we weren't keeping track of I1 correctly. That was probably what we were doing because it wasn't paired inward, or it wasn't paired with the result. I think that's what was going on. Yeah. Anyway. Like we weren't kicking off the recursion correctly, basically, whenever I wrote it before. Okay. Here we go. So relabel function works, but it would be rather ugly in the eyes of many functional programmers. The main issue is that you are mixing the logic of the program, which is simple and recursive, with its plumbing, which handles the index at each stage. And that's why we would use a go function, I suppose. Anyway, passing and obtaining the current index is quite tedious and at the same time has terrible consequences if it's wrong, which we did last time. If we accidentally switch I1 and I2, for example, this function will return the wrong result. In order to separate out the plumbing, we introduce a type synonym for functions that depend on a counter. Okay. This way, the type of relabel becomes tree to with counter tree A. So we'll rewrite it again. Okay. Okay, so it says now let's look at the pattern we find in the node branch, which is this pattern right here. So we're gonna write a function called next, which takes a with counter A. Does it look familiar? Oops. Wow, it's really MA. Well, we want to use fmap. Book of with counter. Exactly. That's funny. Okay, so let's write it this way. So next, f, which is a functor, and what's the other one? G. I'm trying to write it the way in the book, but I'm bad. So given an I, we're gonna say let okay. Oh. Can we just actually get rid of that? Um, how does it want to fix this? Oh, I'm dumb. Why does this take 3 things? With counter. Right. With counter needs to take an integer. So this is some integer. Okay. And then G takes G is also requires an integer. So we give it r, which is the next state, which is the next with counter, and our integer. So this should be, I mean, that should be the a with counter b, yes? What is it? Yeah, and then r should be with counter a, I suppose. It's just an a. Yes. It's this here. And then we pass along its integer to fully evaluate the with counter. Right. Okay. I think so too, actually. And this is really like, we can write it really explicit. Do we really want all of those characters? Maybe. Oop. Meh. Those names are in there, so that's fine. I think, okay, I think I know what's throwing me off here, is that this is not a new type. So there's no constructor. It's a type synonym. I think that's what's throwing me off right now. So what if we do it like, oh, this has to be a data constructor? Wait, what? Why? No, I think I have. Oh, right. Thank you. I was just thinking, I almost got there. You beat me to it. By the way, what's going on, BFG? How are you? Okay, so let's see if this helps me. Maybe this hurts me. I said like this is gonna help me, but I don't know, writing it a different way is probably a good idea. Because now we have to write So it's really our monad of A and our... I mean, we know it's called a monad here. And now we're going to have our with counter. No. And then I need... Do I need these parentheses? Probably. Yeah. Or I can put a $sign here, I think. No. Now, did this help me? Not 100% sure. But I kind of want to write it this way. We've seen this before. Whether we remember it or not is a different story. Because we've done state before. We just didn't call it next. We just implemented bind. Okay, anyway. I'm kind of happy I did that. Not 100% sure yet. Okay, some notes about Scala, which we're going to skip. Because we've already decided we don't like Scala. Well, it's not... I mean, I don't have anything against it. I just don't know how to use it. Where'd that come from? Oh, I guess this is the same as that. Yeah. Okay. We could turn on the tuple sections thing and do it this way, but I think this is fine. I mean, next is really bind in this case. Well, it's just bind. Okay, so there we go. And then we can rewrite. Why do I keep writing that? Okay, don't think about this. Just do it. I'm gonna have to think about this more. Oh, right. I need to relabel L to get my with counter tree, and then I can do this. Right. And we need to give it a function. Right. Oops. And then we create node L prime R prime. Sure. Okay. Let's call it something else. I don't know. I can't think of a better name right now. Oh, I'm done. Ignore me. Okay. Okay, so now we have... Yes, it is. So the reason it is not super obvious to me. So I'm going to work through, like, thinking about it. Well, I think it's correct. We can test it real quick. Oops. I have a tree. What did I call it? A. Let's change this name to example, because it makes more sense. Okay, so stack REPL. So we have example and a relabel example 0, 1, 2, 3, 4, 5, 6, which is exactly how that should happen. And we have relabel with example. Oh, you just need a deriving show. Or we can just eval it with 0, right? Wait, what? No, something's wrong. Yeah, now I'm confused. Hang on. Well, first of all, yeah, I'm doing a lot wrong. I'm doing a lot wrong. Sorry. Why this compiles is confusing to me, though. Although maybe the type is dependent completely on this piece. which I think it is. Oh, that's backwards. Should be. Um, what am I doing wrong here? Leaf. Right. Yeah, that's the problem, isn't it? Yes. Yes, yes, yes. So we gotta fix that. For that, let's do some. Okay. So that's all I need. I thought I needed more than that. Yeah. So I'm confused though. This should be X, shouldn't it? No, because I want this paired here. So what's the return type here is this. No, it's that. There we go. Okay, my bad. My bad. Okay. So let's think about this again, just very, very carefully. So this is waiting to be what is the type of this? It's got to be with counter tree integer a. Then we say next, which is again just bind. And we're taking a new a. I don't know why this is very unintuitive for me all the time. When I see it in bind, it makes sense, but when I write it this way, I have a hard time. Well, I don't know. I probably have a hard time both times. Oh, I don't like that. I don't like that one bit. Does it always do that? Oh god. Please no. That's really hard to read. Okay, trying to think out loud. It's not working. Okay, so but this whole thing is waiting for input, yes? Right, I still ran it correctly, I think. I still need to run something like this. Yeah, if I do this, it's gonna give me, you can't see it because it's still waiting on my integer. Okay, I think that's helpful. So at the end here, you're creating a give me an initial number and I'll give you back a with counter paired with that number. Yes. Okay, well, I'm still not 100% on this. I mean, monads are hard, yes? I think we can agree on that. And this one's particularly tricky because it's a state, so I'm hoping that, and I had trouble with state when we did it before, so I'm hoping that we can do that or deal with that. Do. Okay, so yeah, the previous example uses a concrete type with counter to maintain an index in combination with an actual value. But in the same vein, we can keep other kinds of state and thread them through each of a series of computations. The following type synonym has two type variables. The one is the state itself, and the second is the value type. Okay, so now we're gonna rewrite pure and bind with a different. Oh, I can't use a new type here. So why should I use a type here and not a data? Is there a reason for that? So book has, oops. Book has this. Why should I use that and not data? I mean, the only difference is that I have a data constructor. Is a type alias somehow more performant? Or are they exactly the same? I don't know if anyone has an answer to that, but that's fine. Let's do this with data because we normally see this with data. Wait, I can use, I'm confused. I thought I could only have one modifier here. I guess I only need it. No. I'm confused. That's okay. I thought I could only have one type parameter for a new type. Am I just insane? I might be insane. It's entirely possible. By the way, I'm not sure if chat is busted or you guys are just quiet tonight, which is fine. But if for some reason it seems busted, just Discord me, because it hasn't said the right number of viewers or anything today, and it was being really funky at the beginning. Okay, so I think he was just using the type, so you only have to change the you only have to change the type definitions, but now we physically have to rewrite it. It's just one constructor and one field. I see. Okay. The rule isn't the parameterization, it's these two pieces. Got it. Thank you for that. So now we're just gonna change the name. So bind is going to take a state SA No, I don't need to do that. I just need to write state Oop, I accidentally deleted it over here. Okay. Here we go. Yeah, okay. I feel better about that. Rewriting that felt a little more comfortable. I think my biggest issue right now is when it comes to this kind of stuff, I don't practice enough. And so this concept of using, like, dealing with state just doesn't stick with me. Which is good that we're doing this book, but then even after I finish this book, I need to I need to practice or I'm gonna have trouble. Then the only thing we have to change up here is basically this with counter and that with counter, and we're basically done, right? And these next to binds, and this pure to pure double prime, I suppose. Okay. Oh, that was an exercise as well, so I should write that. Exercise 1.1. Okay. So, in the functional world, we refer to the pattern that state embodies in several ways. We say that state adds a context to a value. Context? Well, the context is not seen here, but it's the other piece to this tuple. An element of type state SA is not a single value, but rather a transformation of a given state into a new state and a result value. We also say that next makes state work in a sequential fashion. The result of one computation is fed to the next computation in the sequence. Got it. Binary trees are simple data structures, but in Haskell there's a simpler and more essential container, lists. The special syntax for list is baked into the compiler, but we can think of the type list A, or for Scala list, like written out A, as being defined in the following way. So I think all of us know this, but so that's approximately the data type for a list. Ugh. That's one thing that always annoyed me. Okay. There's some stuff about Scala subtyping, which I'm going to ignore. The first techniques that a functional programmer learns when working with lists are pattern matching, defining different branches for the empty list, and the cons with a head and a tail, and recursion. Using the result of the same function on the tail of the list to build the result for the whole. So, right, as a reminder, oh, I should do it just this way, huh? No, I'm okay. Yeah. So we all are pretty familiar with this, I think. What is this? Okay, so the Brittany formatter puts spaces in both places. I'm okay with that. I don't love this continuation though. I don't know if there's a way to tell Brittany to do something different. Brittany, you need to fix your formatting. That's not serious. That was like supposed to be a joke, but it was bad. So ignore me. So write a function plus plus that takes two lists and returns this concatenation. Sure. So concat list. It's funny how this stuff doesn't, like, it's just not in my memory, which I suppose is a good thing, because practice, again, is good. Okay, so if we get this, we want to do that. But we're never going to get... No, I can't do it this way. I'm missing a pattern. Don't give me the answer, I'm just being stupid. Dense is probably correct. So we want to... No. TXS. And then... Yes? I think so. Well, let's not do that because I have to change the font size every time. I think that's right. Yeah, okay. Yeah, wonderful. Oh, except it was supposed to be a... It was supposed to be another function, but I would only be able to define plus plus if this... How? I need to empty the first list first. Otherwise I don't catch the case where... Maybe I'm misunderstanding what you're saying. It has to take two lists. Right. But that will get taken care of immediately, right? That's part of the recursion. If this is empty, then we'll just hit will we? I mean, let's test it. I might be missing a case. You could be right. I might be missing a case, or my logic is incorrect. If this is empty, do we do recurse forever? No. Yeah, because it recurses through. Let's see here. So eventually we get. Wait, how does that work? I'm actually a little. There's no need to recurse there. Oh, right, because I see what you mean on the right side, because T includes the empty list. So we're done. I got you. Sorry. So this, I see what you're saying. Now, this does fail, I think, if I only give it one element, right? I think it does. I think this fails. No, that's fine. Okay. I thought maybe I was missing one case, but apparently not. I now understand what you mean. Sorry about that. Okay. This is such a boring way to look at lists. I prefer to think of them as magical devices. Incredible boxes. Oh yeah, I don't need to. Yeah. Use Foldar. What? Let's see what this does. Well, okay. Fine. That's totally fine. We're gonna leave it recursive. Because it tells us, well, to be fair, it doesn't tell us to, does it? Technically, it doesn't tell you to, um, no. R. R is in right, and L is in left. Right. Left, right. Ugh. Let's write it that way. That's probably better. Okay. What next? Map. Oh, HLint is absolutely amazing. Like when we were doing that one plugin, I feel like I forget what it's called. That Dram Forever plugin with VS Code before, not having HLint was a huge issue. Like using HLint is extremely important. I think we're gonna need to map prime this. You learn like very, very good stuff. I mean, makes perfect sense when I look at it, but I would never have written this offhand. Unless someone was like, oh, you know, you can write that in Fuldar, and then I probably would have figured it out. There's already a map defined, right? Yeah. That's, I think you have to write map prime. So we're gonna have an F, we're gonna have an H, and a T. Use map. Thanks, Ancient. You're right. I should use map. I wonder if it just looks at the binding and just realizes the only possible way to write this is with Fuldar, or at least one of the possible ways to write it. Oh, also, we need a space there. Is that correct? Yes. Okay, there's map. I don't really love that this is like portrayed as magic. This isn't, I don't think that this is magic. This is like extremely important stuff. Anyway, that's besides the point, and magic is fun, so I guess. So he introduces a singleton function, which is just pure for lists. So we know how to do that. Just take an element and embed it into a list. Okay, so note the similarity of the type with that of pure as defined for state contexts. In both cases, we get a pure value and inject it into either a context or a magical box. The third spell is my favorite, concat. So, I think most folks probably know what concat is, but we'll write it anyway. We'll use we can write concat like so. You can also write the more recursive definition using this and something like this if you want, but you don't have to. It's kind of funny. So what's so magical about this function? Well, it takes a list of lists and somehow manages to turn it into one flattened list. I picture leprechauns obsessively opening the inner boxes and throwing their contents back into the outer box. Kind of a fun picture. A list is a kind of box that supports 3 operations: mapping a function over all the elements contained in it, functor; creating box from a single element, also functor; flattening nested boxes of boxes into a single layer, bind. Well, part of bind anyway. Both, maybe, I don't know, that's an option. Kind of fun. Got a title containing both Scala and Haskell references. Okay. One of the more widely advertised features of functional languages but in fact coming from their support for algebraic data types, is how they avoid the billion-dollar mistake, that is having a null value that fits into every type, but which raises an error when you try to access it. The billion-dollar mistake. Wonderful. Since creating new data types is so cheap and it is possible to work with them polymorphically, most functional languages define some notion of an optional value. In Haskell, it is called maybe. Scala, it's called option. Swift is called optional. And in C#, we have something called nullable. We know this. The primary use case for optional values is the validation of user input. So we'll create a record class for the classic person. No. Also no. I feel like it just got dim in here. Maybe I'm losing my mind. Okay. There's a person. So now we can have a validate name. There it goes. But we're gonna throw away the problem with the billion-dollar mistake and just use it. Oh, that was hard. I gotta fix those colors. Those colors are difficult. Whoops. Okay. Computer's not blowing up, but it feels a little slow right now. Does anyone else feel like the type completion feels a little slow? You know what's funny is I was working with a problem like this today. Okay, so how do I get out of this? Because the only way I've figured out is just doing escape O. Nothing. I had this exact problem today, by the way. Very similar anyway. I'm writing a function for that project that we talked about before that basically reads a file from the file system, but there's a few things that have to be true. First, it has to be there, and then if it's not there, you can't read it. If you read it, you need to validate it in two ways. First, it needs to contain a valid UUID, and what else does it need? It needs proper permissions. So it's kind of like this, where you have these nested case statements. I think that's right. Okay. Except that's it. Well, that's happening in the IO monad. So it says this solution clearly does not scale. As we introduce more and more validations, we need to nest the branches more and more. Furthermore, we need to repeat the following code over and over again. Nothing, nothing, right? So the common pattern is basically something like this. Where, you know, this piece is basically like the next action. Okay, so we're gonna write this function. Look familiar? I think. Um, no, this is not state. This is different. Okay, so there's got to be a. Oh, does that need to go all the way over there? I think it does. Let's do that again. Wait, can't I simplify this? It's a lot simpler. Yeah, perfect. That's basically what they wrote, but this is just simplified. Wonderful. And then our now we're gonna have validate name then oh. Okay, cool. So there we go. That's the validate name using the other named bind. The then underscore version of bind. Okay, so the key here is that these next and then functions look really, really similar. Their types we can line up. Okay, so clearly these are quite similar. So in some sense, being optional is also a context, but instead of adding the ability to consume and modify a state, it allows failure with no value, in addition to returning a value. In a similar fashion, then sequences computations, each of them possibly failing into one complete computation. Maybe may also work as a box that is either empty or filled with one value. We can modify such a value if one is present as follows. They just define the map and the pure function, or it's really fmap and pure, but fine, we're okay with that. But what is more interesting, we have an operation to flatten a box that is inside another box. If either the inner box or the outer box is empty, there is actually no value at all. Only if we have a box containing a value can we wrap it into a single box, right? So let me write that, because that's kind of a mouthful. I think everyone can probably picture it, but there we go. So that's right. A box within a box that contains a value. So it's extra clear. Okay, let us play a game with boxes and contexts. Is it possible to flatten two layers of boxes by using just then? Following the types points us in the right direction. So I'm surprised this isn't an exercise. He just writes the answer. But I think that it's just no. Oh, that's not right. It's like that. Okay. Or then MMA id. Fine. Either way. I like writing it that way because, you know. I don't think I need to expand this. if this function returns itself, wait a second. Wait, why does this work? Right, because we have this embedded just. Exactly. If we write the type signature, it's probably a lot easier to see. Yeah. So if we apply identity to this function, you're left with this piece. So you get this to itself, and then that's just itself. Okay. I was like, wait a second, why does that work? Yeah. Okay. Cool. Now, dear reader, you may be wondering whether we can go in the opposite direction. The closest type to then is map with its arguments reversed. Imagine that we have a function f, a to maybe b supplied for then, but we give it by mistake to flip map. In response, the type variable d in the flip map is instantiated to maybe b. This implies that flip map f was O. I don't know what O is. Has type maybe D. Not exactly what we aim for. Is there any way to flatten those two layers? That's exactly what flatten does. What? Am I missing something? I don't know where this O comes from. But okay. I think we're okay with this. Oh, I see. We could rewrite flatten, excuse me, not flatten, then in terms of flatten and fmap. Although technically we haven't defined fmap, but it's available to us because we're using maybe. I wonder if it was meant to write map and not fmap. But that's okay. Not too worried about that. Okay, so 2 for the price of 1. The definition of flatten in terms of then and vice versa does not depend on any specifics of maybe or option. They are just particular usage of those functions. This suggests that we could do the same for the other 2 data types introduced in this chapter. Let us begin with the version of flatten for state. I mean, this is exactly the same as before. I'm gonna guess that that's an I. Erithu. Hopefully I'm saying that. It's either Erithu or Urgedru. I don't know. You can tell me which one it is. Is it a hard J or a soft J? I? Anyway, thank you so much for following. I really appreciate that. We are here usually Tuesday, Thursday, and Friday from about the same time. We do 7:30 to 9:30 typically, and we stream Haskell all the time, so feel free to come hang out. Do you write Haskell? You might not be interested in talking, which is fine, but you are. We're a friendly group, so tell us what you like to do. Okay, so So one of these I have to evaluate. Did I name it something else? I named it bind. I changed the name. That's on me. I probably need to evaluate somewhere. This is hard to read, so just gonna clearly doing something silly here. A is an embedded state. So if we take SS, why is it a with counter? What? Where is this with counter coming from? Did you see what it said here? Why is it called with counter with counter? That type doesn't allow changing the inner type. I'm not trying to change the inner type. I'm confused at why it, first of all, why HIE says what it is. I don't know why I'm not getting diagnostics anymore. Anyway, that type flattened state is fine. Do I need to just like write id and then oh, okay, something's wrong with bind. uh Goku, thank you so much. Thank you so much for the follow. Really appreciate it. This type is too restrictive. Is it? What if I just fun? So what's wait, what? Okay, I see. Well, because this is usually the way I would do this. I see. Interesting. Okay, so you gotta think about this a little more carefully. So the function, right? The function doesn't produce it's another A. It can produce a B. I see. Good call. Good call. So the only way I could have made it work is, oh, I couldn't have possibly made it work because there's no listing of the other type, T or B or whatever the hell you want to call it. Interesting. Okay, that makes sense though. I get it now, but um, it would have took me a while to understand that. Thank you. Yeah. Okay. I'm glad you saw that. Did you just know when you saw that error? How long did it take you to realize that? In the book, he didn't write a type signature, so I just wrote it incorrectly. Or maybe he did. Let's see. That was from the other next. I'm trying to remember if it was written in here. Oh no, we rewrote it, so that was my fault. On me. It's usually on me, so not a big deal. Yeah, I'm okay with it. I don't understand the point here. Okay, so the corresponding operation here for lists is better known than flatten for state computations. The signature of the function is oh. Which is a concat map. Okay, you thought about, okay, fair enough. As long as you weren't just like, yeah, that's super obvious, then I don't feel as bad about it. But I should have, let's look at the error again. Let's see if we can come about this logically from the error. Well, more logically. 55. Well, okay, and then we'll just close this and look at this. Okay. Yeah, this error message not super helpful. Okay, cannot construct infinite type errors are basically a special type of cannot match types errors. I see. Yeah, that's not a super informative error. But good catch. Oops. Okay. Anyway, that's concat map, better known as flat map in Scala. I don't know why I couldn't think of the word Scala. We sort of know what concat map. Well, oh my gosh, this cat just knocked some stuff over very loud. Okay, so let's just look at a quick example of concat map. So we can write concat map 110, which is like the numbers 1 through 10. And then we're gonna take x and add 1 to it and add 2 to it. Bloop. Wait. This isn't it supposed to be this way? Yeah, okay. It's backwards in the book, but I think that's because he's defining it this way. Yes. Okay. So he defines it concat map XS, which is the list, and this is not 1 through 10. This is 1 and 10. 1 through 10 is this. My bad. He flips the definition. So we're using the concat map that comes in the standard library, and he's using a custom defined concat map, which is fine. This example suggests another view of the list type not as a box, but as a context. In the same way that maybe option adds the possibility of returning a value, list adds the ability to return multiple values. So the fact that you can always define a box-like interface from a context-like one and vice versa shows that the two interfaces are just two sides of the same coin. Define a box-like interface, which I guess is fmap, and a context-like one, which is the bind, I think. In fewer than 10 pages, we have been able to find 3 data types, state SA, list A, and maybe A, that share a common abstraction. This common interface is what we call a monad. At this point, Haskell and Scala diverge in the names assigned to the generic functions defining a monad. I'm not going to discuss the differences. In Haskell, you have... We'll talk about Haskell. So you'll have class, monad, well, applicative, and you have these things, and then you go up the chain all the way to fmap, but we'll just define these two just for now. The definition of the generic interface of the monad highlights an important point. Monads are higher-kinded abstractions. Being a monad is not a property of a concrete type like int or bool, but a type constructor like maybe or list. Haskell's syntax hides this subtle point, but Scala is explicit. We don't. As an example, here's an implementation of the interface for maybe option. In the Scala code, we use the type class pattern. Don't care. Okay, so just as an example, you can say instance monad maybe where. This might complain, but where did that come from? Then yes. And this is gonna, oh, I can't click with a mouse. What am I thinking? Yeah, so anyway, control GC. So we can't define this twice, so that's why we can't do this. But anyway, that's an example of an instance for monad for maybe. Okay, before closing this chapter, we should remark that part of our definition of monad comes from a more generic abstraction called a functor. Functors encompass the simplest notion of the magic box, and I don't like the magic box. It's not my favorite term, but that's okay. Functors encompass, I already said that. In other words, a functor provides a function fmap, think functor map or map, but nothing. Whoa. A functor provides a function fmap, but nothing comparable to the monadic return. Sorry. So for functors, you have functor m, where fmap is fa. Nope. So the functor here, oh, I wrote m, it's supposed to be f. So the functor here is that concept of just a box with something in it, and then you lift this function into the box. That's the way I like to say that. Or, well, that's the way Haskell people say that. You lift the function a to b into the box fa. By calling fmap over a function, you turn it into a new function that operates on elements contained in the functor. This is called lifting, to operate at a higher level of abstraction. For example, so that function is a humble function that operates on numbers and thus might have the type int arrow, int. Sure. If we write fmap plus 1, this function may now map listInt to listInt by executing the function on every element, or maybe int to maybe int by modifying the value, only if there is one, or even state sint to state sint by changing the value to be returned from the computation but keeping the state untouched. In fact, this way of looking at functor leads us to the discovery of another interesting structure, the applicative functor. But for that, you need to wait until chapter 3, dear reader. I like the way he writes, dear reader. We already know what applicative functor is, so we'll just put it here, but it is in GHC 8. I don't know when this came into GHC exactly, but it's now required of a monad. And hey, don't do that. Break this book. I'll be very mad at you. Stop. Cat, sorry. Oh, I spelled that wrong. My bad. And we have a function, this one, which has type f, a, b, f, a, f, b, right? So now you have a function in a box, basically. So function in a box, you need to get that function out and then lift it into aft. Or I suppose one could argue there's no lifting because it's already in the box. I'm not sure how that argument works. But anyway, this is kind of the order of operations. If you have a box that you know is a functor, a applicative, and a monad, you just implement them one at a time. Okay, so with that, I think we are done for the night. Because I finished a chapter and I don't want to start a new chapter and like move on. So I'm gonna check in this code real quick, but if you have any questions about anything, feel free to just ask me now. Yeah. So as a reminder, so I don't forget, we are working on this book. You can get it on Amazon. The Kindle version's a little cheaper than the paper version, but I will say that wow, all of a sudden I see 7 people here. I think the viewership just updated. So thanks everybody for watching. I didn't even notice that. I did see a few follows, but it said 1 the whole time. So hey everybody, I didn't realize you are all here. I knew BFG was here. He was helping me, and we have some followers. So anyway, this book in the Kindle version, I would argue, is not even worth it. And the reason I say that is the formatting in the Kindle version is not very good. So I can show you exactly because you can see it. If you look at this, check this code out. It's really, really ugly. It's kind of hard, probably hard to show you on screen, but I'll try. Hang on, I gotta put this in front. So we'll see the difference between the two, maybe. Over other way. I don't know how readable that is, but I'm just trying to point out that typeface looks a ton nicer. So, you know, if you really are, I mean, I'm a super huge fan of textbooks. So, you know, if you're okay with textbooks and would rather read it in paper, it looks nicer physically. So just so you're aware. And it's not terribly more expensive. Okay, I don't see any questions from anyone. So, as usual, I will be back on Thursday. And on